we have seen that the conformational analysis is a computer-aided drug design as a part. We are doing as a systematic evaluation of the 3D spatial arrangement of a molecule atoms, that is ligand atoms, resulting from the rotation around a single bond. So we are rotating around a single bond and keep on doing the loci minima and global minima. Why? This is going to identify the bioactive conformation, that is the specific structural shape of the ligand adapts to bind optimally to the target protein receptor. So this is where we want to see the what is the optimal structure conformation. The conformation is nothing but the three-dimensional array or the position or the size or the shape of the ligand that is going to help us to fit in the receptor. Because the molecules are dynamic and explore the complex potential energy surfaces because they are having some charged species because of the functional groups present in them. Understanding these geometric state is very much critical to fit into the space of the pocket of your receptor and predicting the drug potency, selectivity, and pharmacokinetic properties. So this is we are doing in advance before making a molecule and finalizing the molecule so that we are finding a failures in advance. That's what we are doing at the last stage of your drug design. Then we are going to entering into the development process and we are going to entering into the marketing stages and post-marketing stages. It means these are all doing bench work, that is in silico approaches, making ourselves confident. The core objectives of this particular conformational analysis in the drug design, and what you are going to have a lesson objective also, and what you are going to get with this particular session is bioactive conformation identification. You can do it by locating the specific affinity shape that fits into the receptor site. How to do it? That one we can see. Another one is the energy minimization, calculating the strain energy penalty between the molecules global minimum freely floating in the state and its bound state. Most of the times, the global minima, when it is unbound state, it may be lower. But when it is fitting into the receptor, the molecule will maybe getting a strain and in energy states will be different in the bound state. That is also important. So we are going to find out with the conformational analysis and going back to after coming to the energy minimization to the conformational stage, we are going to do the docking studies and see the bind state status. Similarly, we are going to use the same pharmacophore mapping also. So aligning the structurally diverse molecule based on the shared 3D arrangements of the essential chemical features, wherever you don't have structure of the protein in your hand. So you don't have the structure of the protein, but you have got a ligand that is acting in the treatment of the disease. You know one shape of the ligand. Similar, you want to bioisosteres and find out what is their shapes and conformations that are going to fit, so that you are going to generate a new lead, new pharmacophores, and you are going to do a ligand-based drug design and create a own patents and own market, because of you are not infringing anybody's, you are not copying anything. That is the reason this conformational analysis you help is. This is what the outcome is. After learning this particular topic, you will be able to design and the conceptualize how to get a new moiety with the existing moiety, and wherever the moiety is present, how they are behaving in the unbound state and the bound state, and whether the status of the conformation after conformation, whether it is going to work or fits into the receptor so that drug likeliness is present or not. These three are the outcomes of this particular topic. Now, conformational search methods are divided into majorly into three types. One is a systematic search, another one is a random search or just stochastic search. Don't get confused, both are different. One is selecting randomly. That may have, you will come to know it will fail as a drug or it will not, it will work as a drug, yes or no, like that. It will be present because it is random. We are picking up and doing it. Whereas the stochastic models are the one, they are the predetermined, and their futuristic models, they are going to yield your confirmation is going to work. If it says it won't work, and it will not say, it will not proceed, and it will say it is going to work, it will proceed. In the stochastic, it is having some logic behind it instead of like a random. There are two types in this one. One is a Monte Carlo and the genetic algorithm. We call it as a GA. So the third methodology is a simulation based. In the simulation based, we are going to see the molecular dynamics and metadynamics, where the structure is in the dynamic state. We are finding its energy components, how many seconds are the duration of the time the ligand is going to fit into the pocket. And that is the receptor we can see. The first one is the systematic search. The systematic search is also called as a deterministic search method in the confirmational analysis we are doing. So the first one in this particular case is the grid search. In the grid search, incrementally we rotate all the rotatable bonds by the fixed by a fixed angle. So say for example, your ligand is containing 3 rotatable bonds. So the 3 rotatable bonds, you are going to have a rotating in all bonds and see the local minima and the global minima. So what is the limitation of this particular method? It suffers from the combinatorial explosion problem because it is having 3 rotatable bonds. We have got rotations, number of rotations we can make in 360 angle. So your configuration will be n to the power of k configuration, where it is number is very high, because the number n is the steps and the k is the number of rotatable bonds. So the number n is the steps is depending upon how many angles, after how much of the interval of the angle you want to repeat this particular iteration process. It can be a 30, 60, 90 or 10, depending upon the n, your this configurations with number will also be increased. That is the biggest problem. It is computationally impossible for compounds with greater than 6 rotatable bonds, because when your rotatable bonds are very high in this moiety and you are going to determine in all the angles, it takes very longer time, and it is very complex also. That is major limitation. The second one, what we are going to have is a stochastic method. So in the stochastic method, we are going to use, it is a part of randomization only, but we use the Monte Carlo simulations. So the randomly searches the torsion angles, evaluate the energy changes, accepts or rejects the new shape based on the metropolis criterion. That is depending upon your delta E. Delta E means energy minimization. So in the Monte Carlo simulation is based on the taking the previous data and take a decision and reiteration in the next, so that it will have an energy minimization with the metropolis criterion, like e to the power of delta E divided by kb into T. T is the temperature, kb is the constant, delta E is the energy minimized state, change in the energy. So it accepts when the energy minimized and rejects when the energy is maximized in the Monte Carlo simulation, and takes those structures only for the confirmation analysis. The second approach in this particular case, stochastic method, is geometric algorithms. In the geometric algorithms, it treats the torsion coordinates as a genes. We know that the genes will be having some sequences, and it is going to yield a corresponding proteins based on their code. So similar manner, in the genetic algorithm, it evolves the populations of the conformations via crossover and mutation operators, selecting for the low energy variants. Just like our genes are getting varied with respect to the protein what is required to be synthesized, in this case also the genetic algorithm makes changes in its structural setups, so that it will be having a minimum energy variance. So this is also a random process, not like a organized manner in the systematic manner in the first method. So the third one is the distance geometry. So in the distance geometry converts the 2D connectivity. We have got a bond angles, bond lengths into a matrix of upper and lower interatomic distances bonds. So when you are changing their angles, you are going to change your interatomic distances and bonds also. So randomly sampling the coordinate that satisfies these bands, which is having a low energy states, and we are going to use that length, bond lengths, that is going to have a low energy states fit into our requirement. So this is actually what the called as a stochastic search leads to the confirmation of your molecule for finalization. Confirmational decision you can take it. The third approach is simulation and dynamic methods. So in this one, we are going to have a molecular dynamics is the first path. It solves the Newton's law of motion over the time. That is femtosecond steps we are going to take. So what is going to have not like a milli or nanoseconds, it is femtosecond steps which is going to take to track the continuous molecular trajectories and the crossover energy barriers when they are moving in the free space in the molecular dynamics. Most of the times these molecular dynamics will have the water effects also. What is water effect? Wherever there is a hydrogen bonding capacity is present in the molecule, there will be a possibility of having a bond with water, H2O, because it is containing H plus and O. So the O will provide the capacity to the acceptor, proton acceptor. H will be having a proton donor effect. So this water will present hydrogen bondings. And when the molecule is moving, that will move along with this water also, so that it will be shape and its charges are affected. So we take them and also account and track the continuous molecular trajectories with water effect, with solvation, without solvation or solvent effect. The second approach is enhanced sampling. The technique like metadynamics, that is called as replica exchange molecular dynamics, REMD, and accelerated molecular dynamics, metadynamics, apply the biasing potential to force the molecule out of the local energy wells and map the deep energy landscape efficiently. So we are going to mutate the molecule, and it is a form of making rotations, and we are going to forcibly doing this so that the high energy, the local energy, wherever it is having the lowest levels, that we are going to map with the number of rotations when you are going to do. This is actually a meta state. It is not a fixed one. We are keep on doing it and finding it wherever it is finding a low energy states. And we are going to do it very fast because it is in the meta, and we are not having directly into the fixed or the deterministically. So it takes the lesser time. Depending upon our choice of the time and what is complexity of the moiety and what the money we have got, depending upon that, any one of these methods we can select for the conformational analysis. So 22 are there. I will take again attendance. Are you able to see PPT on the screen? Somebody
Yes,
unmute
sir.
yourself and say.
Yes, sir. Yes, sir.
Are you able to see?
Yes, sir.